This section is about logarithmic functions. Now let's start out with a definition. Okay, so we can write it like this. Y is equal to the log to the base b of x if and only if b to the y equals x. Okay, now these letters if, this is not if misspelled. This means if and only if. And that is a mathematical condition where indicates the if-then statement goes both ways. Okay, so let's go this way. If y equals to the log base b of x, then b to the y is equal to x. It also goes the other way. If b to the y is equal to x, then y is equal to the log to the base b of x. Okay, so this is a stronger condition than just if it went one way. All right, now you may have seen this statement when you were studying geometry and using theorems to do proofs and all that. If you haven't, that's fine. It's just I'm not going to test you on it. It's just a mathematical statement, okay? A way to show both direction causality, all right? Okay, anyway, now let's recall, we do have these conditions. B has to be greater than 0, the base must be greater than 0, and not equal to 1, and x is a positive number, okay? Not necessarily an integer, just a number. Okay, now recall an exponential function is in the form y is equal to b to the x, where b is the base. A logarithmic function goes the other way. A logarithmic function is of the form x equals b to the y. So the y in a logarithm is really nothing more than an exponent. Okay? Okay, let's do some examples. Let's rewrite this in exponential form. Now, keep one eye on this statement up here, all right? So if we go up in this general thing, b is the base, okay, so 5 is the base, okay, the y is the 3, and then the x is the 125. So what this means is 5 to the third equals 5 to the third equals 125, okay, and if you think about it, 5 times 5 is 25, times 5 is 125. Okay, so we're taking the b to the exponent, and that is equal to this. So the log of 125 in base 5 is 3, the 3 being the exponent. A log is an exponent. Okay? Okay, let's do this example. Now, before we answer this question, let's take the left side of this and rewrite it, because the radical sign is confusing and annoying and all that. So let's rewrite this as 1/8 to the 1/3 power equals 1/2. And if we write it like that, we have it in a form that's like this: b to the y is equal to x. All right, so if this, now let's go the other way. Let's use this condition where we're going to the left. If this, then this. So rewrite, where does the 1/8 go? Where does the 1/3 go? Where does the 1/2 go? Well, the b is the 1/8, the y is the 1/3, and the x is the 1/2. So if you insert them into this, you'll see that the log to the b, where once again b is 1/8, okay, of x, okay, of x equals y, and we get this. So keep an eye on this and have it as a visual. I like to have it as a visual because it makes then I make sure that I put the right quantities in the correct place, okay, until you get a real good handle on this. All right, now there are some properties of logarithms that you were presented in Math 3, I believe, or perhaps earlier. If not, that's fine. If we have a log to the base b of a product xy, that means we can take the log of x and add it to the log of y. Okay, that's a product property. So you can break up this into a product, and the logs of the product add. Okay, thing that follows from that is the quotient property. The log of x over y becomes the log of x minus the log of y. Okay, so if you multiply, you add the logs. If you divide, you subtract the logs. All right. And then one other thing, and this is a super useful property, the power property, where log of x to the y power, we can pull the y out front and write this as y times the log b of x. This is a very useful property that we're going to take advantage of a whole bunch of times. Okay. Examples of this will follow. Of that situation will follow. Now let's take advantage of, let's use these properties to expand this. In other words, we want to take that 3x to the fifth and y, and we want to apply the log to each one. Okay, now first thing I'm going to do is we're going to apply the product property, and we're going to say this is equal to the log of 3 plus the log of x to the fifth plus the log of y, all to the base 4. Okay. All right, now there's one other thing we can do with this. This is fine the way it is, but the second term, log to the base 4 of x to the fifth, I'm going to apply the power property now. And we're going to take that 5, we're going to pull it out front. Okay. This term, the first term and the third term are okay the way they are, but the second term we can pull the 5 out and we can write it like that. And that's our answer. And that's this logarithm expanded. Let's do the same thing here. So now we have log to the base 3 of this. Now, the first thing I'm going to do is apply this power of 5 to each, to the p and the q to the fourth. Okay, and so we basically pull the 5 inside the parentheses, and that's going to become, the numerator is going to become p to the fifth, and the denominator is going to become q to the 20th, right? Q to the fourth to the fifth is equal to q to the 20th. All right. Now let's apply the quotient rule, the quotient property up here, and so the logarithms will subtract. It'll be their difference. And then one more thing I can do, I can pull the 5 out front and I can pull the 20 out front using the power property. And we write it as this. Okay, well now let's go the other way. Let's condense this all into a single logarithm. Okay. Now, this looks pretty complicated, but the first thing I'm going to do is I'm going to distribute the 2, bring that within the parentheses. Okay. And I'm also going to write log to the base 4 of 25 over 2. I'm going to pull out the 2 up front and write that as 1/2. All right, so we distributed the 2 to get that and that, and then I pull the 2 out front. We're going to write that as a coefficient. All right, now let's take advantage. We want to condense all this down to a single log. All right, so I'm going to use the power property. I'm going to put the 2 back in here and put the 1/2 back in. All right, so the 2 to the log, 2 times log to the base 4 of 8 becomes log 4 of 8 squared. 2 log to the base 4 of 5 becomes log to the base 4 of 5 squared. And then log to the 4 of 25 to the 1/5 power. That's what that becomes. All right, now let's examine this 25 to the 1/5 power a little bit. What this is, the first becomes, okay, this becomes 8 squared is 64, so we got that. Now, and that becomes, I'm going to pull the 2 out front there. I know it's the reverse of what I did there, but you'll see why in a moment. Let's look at this 25 to the 1/2. 25 to the 1/2 really means the square root of 25, and square root of 25 is 5. So then I'm gonna write this 25 to the 1/5. Okay, we're going to write that instead as just log to the base 4 of 5. All right, and now the second term here and the third term are kind of like terms, which we can combine, and that's why I rewrote this, the second term, as this. So we can combine those, okay, into this, minus log to the base 4 of 5. And then one other thing we can do to clean this up, if we look at log to the base 4 of 64, 64 is 4 to the third. And if you look back in the definition of logarithms, that means that the log to the base 4 of 64 equals 3. So this term really is just 3, and we can eliminate the use of the logarithm altogether. All right, so I'm going to put 3 in there instead, and then we get this as our answer. So it's all condensed down to using the word logarithm only once. So we can expand logarithms, and we can condense statements into a single log, all right, using these properties listed up here. All right, now let's get to one of the more useful uses. Okay, one of the more the awesome uses of logs, and that's to solve an equation like this. Notice that the unknown is in the exponent. Okay, we have to get the unknown out of the exponent. And the way to do that is to use this property of logs, the power property. Okay, we're going to take the log of both sides of this equation. Remember, you can do anything you want to an equation as long as you do to both sides. So the log of 41 is the log of 7 to the x. But now, look what happens. I can take that x out of the exponent and bring it out front, like that. And that's really the power of logarithms to solve exponential equations. Okay, they get the unknown out of the exponent. Okay. Now, it's to solve for x, all I really need to do is to divide each side by the log of 7. And I get this. And the log of 41 is a number. The log of 7 is a number. I'm not sure what they are. Don't really know, but your calculator does. So get your calculator out and take the log of 41 divided by the log of 7. And you should get to the hundredths place 1.91. Check that. Make sure that you do. Okay? Okay, other useful things, other reminders, useful properties that we can use from time to time is that this one, the log to the base b of b is just 1. Okay, because b to the first equals b. All right, anything to the power of 1 is itself. Okay, and that follows. If we look at this one now, using the power rule, bringing the x out front to get x times the log b of b. Well, log to the base b of b is 1. X times 1 is just x. So that follows that we get this. And that kind of indicates that the log and an exponential relationship are inverse functions. Okay, and we're going to take advantage of that. Okay, other things that follow are log to the base b of 1 is 0, because b to the 0 is 1. Anything to the 0 power is 1. Okay, and it follows from that. This equals x. Again, inverse operations. Take a look at that. Take a look at that. These are kind of the going one way and then going the other way. Okay, so inverse operations. We're going to take advantage of each of these to solve problems. Now, log to the base 10 is called a common log. All right, because our counting system is based on 10. But that's not really what nature is based on. Nature is based on its own thing. So log to the base e is called a natural log, and it has its own notation, as we'll see. All right. Now, if I write something like this, log with no base down here, if there's no number down here as a subscript, that means it's a common log. It's to the base 10. And 10 to the first is, or 10 to the first is 10, so the log of 10 is 1. 10 to the first, okay, is 10, so the exponent for that is 1. Another way to think about this is logarithms, at least the common logarithms, are a power of 10. You know, so the log of 10 is 1. The log of 100 is 10 to the second. 100 is 10 to the second, so the log of 100 is 2. All right, and numbers between 10 and 1, 10 and 100 have logarithms between 1 and 2. 10 to the 1.4, for example. All right, as we will see. In general, we can get something like that. Again, this is more or less like this one right here. Okay. And once again, we have x to the 0 equals 1, and that's more or less restating that right there. Okay, so let's keep these in mind as we solve equations, such as this one. So we want to solve this for x. Right now, the unknown is embedded within the logarithm. So what we're going to do is we're going to take 10 to the on both sides. 10 to the log of x equals 10 to the 3.0876. Now, 10 to the log of x, okay, that's like this one up here. 10 to the log of x is just x. So those operations are inverse operations. They cancel each other out more or less, and we just get x. And on the right-hand side, if you use your calculator, take 10 to that power, it's 1,223. All right, verify that with your calculator. So by using the inverse operations, we can get the unknown out of the logarithm. Okay. Now, so it's this. ln of x is a natural log. okay, or log to the base e. Instead of writing log to the base e all the time, we just write ln. That's natural log of x equals this. Now the inverse operation for a natural log is taking e to the power. So we're going to take e to the natural log of x equals e to the minus 0.9128. E to the natural log of x, those functions are inverse operations. They undo each other, and so we just get x. And then my calculator, if you take e to the negative 0.9128, locate the e to the x button on your calculator, and take e to that, and you should get 0.401. Verify that with your calculator. All right, now let's take this. So before we can solve for x, we need to isolate this term. Think of this like as 3x plus 4. First thing we have to do is isolate the term with the x in it, right? So we're going to do that by subtracting out the 4. And when we do that, we get 3 log x is equal to 11. And we are then going to divide each side by 3. And we get the log of x is equal to 11/3. All right, okay, now we have this isolated. And to cancel out the logarithm, if you want to talk about it like that, we can take 10 to the. So 10 to the log of x equals 10 to the 11/3. 10 to the log of x are inverse operations. They undo each other. And so the left-hand side just becomes x. And then if you insert 10 to the 11/3 in your calculator, it should say 4,642. Please verify. So what these logarithms do, and this is a very, very common things. One of the uses of logarithms is to get unknowns out of the exponents, and use exponents to get them out of the logs, essentially. Okay. Okay. One other thing we want to do is we want to find the inverse of this. Now remember. How to find an inverse. We're going to use the same technique as we did for polynomial functions. First of all, we're going to write the f of x, inserting the y in for f of x, and then we're going to switch them. X, instead of y equals 4 to the x, we have x equals 4 to the y. And now we want to solve for y. Okay. Well, how do we solve for y? The y is in the exponent. Well, that's why we use logs. So we're going to take log of both sides. Log of x equals the log of 4 to the y. And from the power property, we can bring the y out front and write it as y times the log of 4, and then simply divide out the log of 4. The log of 4 is just a number, but let's keep it as a log of 4 instead of whatever decimal it is, 0 point something, 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 something that never ends. Instead of like writing out the decimal form, let's just leave it as a log of 4. It's more exact. So just divide out the log of 4, and you're done. Okay. All right, here's for you to try. Find the inverse of f of x equals 3 to the 2x. Pause this video and come back when you have your answer. All right, let's see how you did here. So I'm going to write this as y equals 3 to the 2x. Then I'm going to switch them. Okay, now I have to solve for y. So I'm going to take log of x equals to the log of 3 to the 2y. And then I'm going to pull the y out, and I get this, y log of 3 squared. Okay. And log of 3 squared is 9. So it becomes log of x is equal to y to the log 9. Now, if you did something different than that, then don't erase anything right now. Just hold on. Okay. Now, the log of x is equal to the y log of n, and then I'm just going to divide each side by the log of n. Now, alternate solution. Maybe some of you pulled out 2 and wrote this next line. You pulled out the 2 and the y from here. Okay, and then you got 2y times the log of 3. Right? If you did that and then divided out the 2 log of 3, then you would get this answer. But these two answers are the same. They're equivalent. All right, and the reason for that is the log of 9 and the 2 times the log of 3 are the same number. All right, prove that to yourself. Find the log of 9, then find the log of 3 and double it, and you will find that those are the very same number. So you could have this would be acceptable, and this would be acceptable, because they're both the same. Okay, now let's find out the inverse of this. Right? This is different now because the unknowns are no longer in the exponents, instead they're embedded in a log. But we do the same thing. We just first of all write y in for f of x and then switch them. All right. Now, before we deal with this, we have to isolate this term, and the first term over here, and then where we do that is to subtract out the 1. So to subtract 1 from each side, and I get x minus 1 is equal to the log of y. And then to undo this, we're going to take 10 to the on both sides. 10 to the x minus 1, 10 to the log of y. Over on the right-hand side, those two undo each other, and we just get y. And so our answer is y equals 10 to the x minus 1. As a final example, let's find the inverse of this. The natural log of y is equal to 2 times the natural log of x. Right? So it's already, y is already written in there. So now let's just switch them. Okay. And then solve for y. By first, let's take, right now, let's e both sides. Okay. Let's e to that. Oh, first of all, sorry, my bad. We're going to take the 2 in for that. All right. And then I'm going to e both sides. E to the natural log of x equals e to the natural log of y squared. The e to the natural log of x cancel each other out. And then finally, I can solve for y by taking the square root of both sides. And I get square root of x. Okay. That's not the only way to do this. Instead, if you wanted to isolate the natural log of y first, you would divide each side by 2, and you get 1/2 of the natural log of x, which you would then e it, and you would end up in the same place. This is perhaps a little bit easier way to get to here, but if you did it a slightly different way, you should still get to here. All right. Okay, and then so that's using logarithms, and logarithms are very, very useful to solve problems. All right. So go ahead and have fun doing the practice problems.